Hello. Okay, hello, my name is Karatekin. I'm from Royal Observatory of Belgium. I'm going to give this talk on behalf of Hera Working Group 4 on proximity operations. And I will be talking about mission and payload operations of Hera. You have seen this chart several times today. I would like to just insist on the fact that when Hera will arrive around 30 kilometers, it will start the global characterization. And about 10 kilometers, we are going to release the CubeSats and do the multi-point asteroid investigations. Then we decrease the orbits close to the surface from 5 to 1 kilometer to look at the detailed characteristic of the surface and the crater, and also to show and demonstrate the autonomous navigation. Here, a spacecraft will have an asteroid framing camera, which is the heritage, already as a flight heritage, this instrument, and it will be provided by Max Planck Institute. Then we have two instruments, micro LiDAR and thermal infrared, under development. And here we'll have also a radio science experiment. In addition, it will carry two CubeSats. The first one is Apex with a visual and near infrared imaging spectrometer, ion mass analyzer, and a magnetometer. And second one, Juventas, with a radar, accelerometers, and a gravimeter. There are already some posters on the micro LiDAR and the radar on Juventas, which are available if you need more information. And the following talks by Graziana and by Thomas will give more information about the use of these payloads for GNC, the first talk, and the second one on the Apex CubeSat. So those instruments all together will help the Hera to reach its science and technological goals. And some of the mission requirements are shown here. For example, we would like to estimate the mass of Didymos by better than 10% accuracy. Investigate the shape of the impact crater with a resolution of better than 10 centimeter. Then using the shape model and mass, get the density. Investigate the porosity through the density and composition of the surface. Then study the size of distribution of the surface and also its strength by using visual images, remote sensing, as well as the bouncing of the CubeSats. Then we'll investigate the dynamic properties. You can see some numbers that we target, and also study the interior and the material transport. The asteroid framing camera will play a major role for these investigations. As I say, this is an instrument already with a flight heritage. Some characteristics are given here. It will have several filters. So the figure here shows the reflectance of the surface of Didymos and the position of the filters as a function of wavelengths. So it will also help to provide information about the surface mineralogy. And depending on the orbits, the distance will change and the surface resolution. These are all given on this table with the footprint size and the number of images that we will need to have a complete coverage of Didymos and Didymos surface. In addition, we have a LiDAR, thermal infrared imager, and radio science. All of those instruments will help to reach the technological goals for autonomous navigation, as you will hear in the next talk. But they will also provide scientific inputs. For example, LiDAR will provide information on relative velocity, reflectance measurements, and help to determine better the shape model. Whereas the thermal infrared will provide the surface physical properties such as the thermal emissivity and thermal inertia. The thermal infrared will work at 8 to 14 micron, whereas the LiDAR will be at 1.5 micron. And we'll have the radio science, and this will be done through a coherent transponder on the AIM spacecraft, and it will be in a radio link directly with the Earth antennas. And the idea is to get the GM value as well as the degree 2 and higher gravity harmonics, pole orientations, and rotational dynamics. As I will say also, there will be an inter-satellite link between the main spacecraft and those two CubeSats, and this will further improve the radiometric study. So we have two CubeSats, Juventus and Apex. And today there was a very fresh press release from the ESA site. So you can read more on the ESA web page. It was related to Hera's CubeSats and on Juventus in particular and the radar investigation. So it just came out today on ESA's web page, that press release. So Juventus is one of the two CubeSats, and its main objective is to study the interior structure. It will also provide information on the surface properties as well as the dynamics of the system. It will carry a low-frequency radar, a 3-axis grameter. This will be from the surface, ISL radio link, visible camera for the context imaging, and accelerometers and gyros to measure the bouncing on the surface. This is the configurations with different payloads, and you can see here the big antenna for the radar, and we have also the ISL antennas, and the deployed solar panels you can see in this figure. The Juventus CubeSat will be released from a 10-kilometer distance from the Didymos system. And after the commissioning phase, it will start its global and proximity operations. And this will be from between 2.5 and 5-kilometer distance. We'll use self-stabilizing terminator orbits, as it's shown here. And this is under study, actually, this operation concept. So once it's finalized, then we'll convert those SSTO orbits to equatorial plane, and then circularize the orbit, and we'll attempt to land. And one of the requirements is at least to have 1 day or 3 orbits on the surface of the Didymos. One of the instruments is the radar, which is a heritage from the concept on board Rosetta. It's a low-frequency radar, and in order to have the full tomography, the satellite will need to have the full coverage of the Didymos, as well as will investigate the main body, of course, of the binary system. This is showing this image showing the radar coverage from 5 kilometers as well as from 3 kilometers for 60 days orbiting. And once we have reached those coverage required for the internal study for the radar investigations, then we'll move to dedicated orbits for the inter-satellite link. And the objective here is to get the mass value of the secondary, but also the degree to gravity field with an uncertainty better than 15%. The figure is very busy over there, but basically it says it shows the different perturbations on the orbit as a function of signal to noise ratio, and we have some auto values there showing the sensitivity of our systems. And the short story is we hope we will get the gravity degree T of the Didymos from the ISL link. Then we'll go on the surface and we'll deploy our grameter. At least we want to stay more than at least 1 orbit in order to measure the surface acceleration that will be due to the internal mass distributions, but also due to the tides and rotations. Then we have also a camera for the context imaging mainly. The second CubeSat will be dedicated presentation on that one. I will be very quick. Basically, it will have an imager, magnetometer, and mass spectrometer to study the surface and the interior. It will have a science operation global characterization from 4 kilometers. Then it will go to L4, L5, the Lagrangian points, to have a detailed characterizations. At the end of life, it will attempt to land, but it doesn't include the surface operations. So finally, there is an active groups working, a lot of scientists at Europe for the success of Hera. We are organized through different working groups. This morning you heard talks from the impact simulations. This talk is given on behalf of proximity operations, and we have data analysis, dynamics, and ground-based observation groups. And they're working in coordinations with the DART working groups in order to make happen those two missions and to help to reach their scientific and technological goals. Thank you.
Thank you, very interesting. One question, anyone? So I'll ask a question then. Is there any concern at all from the debris field generated by a DART into the Hera mission?
You mean the
debris field from the collision? Is there any concern?
Not really. It will be a long time, right,
Okay.
in between. So we think that we
It's
don't
a
know,
good thing.
but
It's a good thing.
Yeah.